Correct. Unit 7, lesson 6. Okay, so just a quick review. Kind of just told last period. Guys, if you don't know those values, especially the sine, cosines off the top of your head by now, you're behind. Okay, those need to be automatic. Okay, you need to know that 30 is root 3 over 2 for cosine. You need to know that the 45 is a root 2 over 2 for both of them. I can understand if you need a little time for tangent to code and set them up, that's fine, but they'll come with time as well. But the sine and cosines, we should be pretty automatic. I should be able to say, guys, what's sine at 60? You guys should be like root 3 over 2 emphatically and quickly. Okay, it needs to be kind of a mental thing by now in terms of you've just done it so much. So that's that, whatever, get off of that. But anyway, so we're going to go and talk about the situation where you have a sum within sine. So sine of a plus b. And what they're going to say is we're going to investigate, does that mean it's the same as sine of a plus sine of b? And so we're going to go ahead and just use a value to confirm or not confirm that that's how it is. Okay, so if we take 60 degrees and 30 degrees for b, so sine of 30 plus 60, is that equal to sine of 60 plus sine of 30? Well, sine of 30 plus 60, you might as well simplify that. That's 90. Sine of 90 is? Too slow. 1, thank you. Sine of 90 is 1. You're high. Okay. Sine of 60, root 3 over 2. Sine of 30, 1/2. You can see that they're not equivalent because root 3 plus 1 is not 2. Okay? So no, unfortunately, that's not how they work. Sorry. It would be nice. Probably a little bit easier. Okay, so what can you say about the statements? Not equivalent. I think I spelled that right. Equivalent. Okay. So now we're going to look at what they're telling us to go with. And what they're doing is they're kind of presenting the form to you. So it says, use exact values to verify the following statements. Is sine 60 plus 30 equivalent to sine 60 cos 30 plus cos 60 sine 30? So we know sine 60 plus 30 is 1. We just did that one, right? Okay, well, what's sine of 60? Well, that's the root 3 over 2. Cos 30, that's the root 3 over 2. Plus cos 60, 1/2. Sine 30, 1/2. So if I multiply these, you get root 3 times root 3 is 3, 2 times 2 is 4, 1 times 1 is 1, 2 times 2 is 4. Is 3/4 plus 1/4 1? Wow. Yes. So you verified that that is the correct form. And I think it's really in reality, I think they do that first thing at the beginning. So when you're doing your diploma, when you're doing your final, that you don't just do that simple thing. Okay, it does have a pattern, and they're on your formula sheets. You don't have to memorize these, but right now we're lining out sine plus, sine minus, cosine plus, cosine minus. That's the 4 sum difference identities we're going to get. Okay, we do tangent too, but for the main 4 here. Okay, so then again, they gave us pi over 3 and pi over 6 here, which is also 60/30, but they're minusing this time. Okay, so that does matter. But pi over 3 and minus pi over 6, if you're trying to figure out what that is, we just have to do common denominator. Pi over 3 is 2 pi over 6, right? Pi over 3 is the same thing as 2 pi over 6 minus 1 pi over 6. So what I'm saying is pi over 3 minus pi over 6, you're evaluating pi over 6. Pi over 3, just do fractions. Oh, you see. Okay. You just don't like it. Yeah. Okay. So sine of pi over 6 is 1/2. So we're expecting this answer to be 1/2. Okay. So here we go. Sine at pi over 3. So that's the 60 spot. That's root 3 over 2. Cosine at pi over 6. That's also root 3 over 2. Minus cos at pi over 3. That's the 1/2. Sine at pi over 6 is the other 1/2. So again, this time we get 3/4 minus 1/4. Is 3/4 minus 1/4 1/2? It is. That one is verified. Okay. Cosine 30 plus 60. So now we're doing cosine plus. So that's cosine at 90. What is cosine at 90? 0. Oh, there we go. 0. Good. Cosine at 90 is 0. You're top, so you're in the middle. You're on the y-axis, so your x is 0. So let's look and see what happens here. Cos 30. Cos 30 is, yep, root 3 over 2. Cos 60, 1/2. Minus sine 30. That's the root 3 over 2. No, you're right. That's 1/2. That's 1/2. Yeah. I was getting them backwards. 1/2 root 3 over 2. I just know they're going to be the same. You can see here, you don't have to multiply them. You have the same times the same. Subtraction, that's going to be 0. So that one's verified. Okay. If you did multiply, it'd be root 3 over 4 minus root 3 over 4. And the last one here, we're going to do the cosine subtraction. So pi over 2 minus pi over 4. Again, I'm going to do common denominator. That's the same thing as 1/2 minus 1/4. So I'm going to write that as 2/4 minus 1/4, which is 1/4. So you're looking for root 2 over 2. Root 2 over 2. Cosine of pi over 2 is 0, so I don't really care about this other one. You can write it if you want, but that's going to be 0. Sine of pi over 2, 1. Sine of pi over 4, root 2 over 2. Verified. Root 2 over 2 is root 2 over 2. Okay. Right. Right, but also cos, the other paired. Cos is cos, and sine, sine. But again, you don't have to memorize that. These are formulas you're given, but here's the pattern. So now I was trying to figure out, yes, sine kind of acts normal. Sine plus is a plus of them, and sine cos plus cosine. The minus is sine cos minus cosine, so that's not too bad. But then cos, they're paired. Cos minus sine, sine. Opposite. See, it was plus, so opposite. Then cos for minus is cos plus sine. Exactly. Okay, so what we're gonna do here is we're gonna kind of finish. We're gonna finish and show the work for tangent, how tangent comes about. So what we're gonna do is that tangent a plus b. Okay, we could write tangent a plus b as the sine of a plus b over cosine a plus b. So we're going to try to get to, this is the form we're looking for. So we're just going to do a little bit of stuff here. This is kind of proving, if you get lost in this, it's not super important. It's just as a matter of unwrapping. It's just a big identity, really. Just a big identity. Okay? So, does everybody see step 1 to step 2? So tangent a plus b with the sine cos a plus b. Then what it is, we use the things we just found out. So this is sine of addition, cosine of addition, top and bottom. So we change those to the addition, the sum difference formulas there. So now what we're going to do is, this is the move they do that I think is kind of weird. And this is what kind of happens when it comes to proving things and in identities. You can kind of add things that help you. So what they did was they divided both the denominator and the numerator by cos A, cos B. You can do that because you're doing it to top and bottom. And so the reason this helps us, it's a cos A, cos B, and a cos A, cos B here. When I simplify, sine A, cos B, I'm going to write that singular over cos A, cos B, plus cos A sine B over cos A, cos B. So that's the top. So I just broke this up, 1, 2, into 2 fractions of over cos A, cos B. And you kind of see how that's going to help me. I'm going to get some stuff that cancels. That's a strategy they use to help get to where we're going. So that's kind of like it's using a mathematical operation that's allowed to prove the identity, which is something that you can't just say, I do this because. There's not a reasoning for it.
It's not because it's in the denominator already?
No, it's not in the denominator already. Well, you still can't see it. You could say maybe, but like this one doesn't have one. Yeah, there's really not a direct reason to why to use cos A, cos B. That's just for this proof. And again, this is a proof, so this is not something that you're expected to do. Okay? So, like in Math 20, we put the quadratic formula. You never have to do that on an exam. But this kind of helps with identities a little bit. Okay, so anyways, yes, the cos A, cos B is just kind of, kind of came out of nowhere, sure. So cos A, cos B over cos A cos B minus okay, so obviously there's a lot up here, and it's going to go away quickly. Okay, so if I go through each piece, this piece has a cos B canceled. This piece has a cos A canceled. This piece, everything canceled. Okay, this piece, nothing canceled. So what is left? Well, what's left here is sine A over cosine A, which is tan A, plus sine B cos B, tan B, over, when stuff cancels, it's not a 0, it's a 1, minus, now what's this going to be? Sine A cos A is tan A, sine B cos B is tan B. Right, so it's tan A, tan B, like next to each other, and then that's what they have here. So we just got to essentially, really? I think the only thing that doesn't make sense is why the cos A cos B came in. All the simplifying should make sense.
What I want to know is why on the top one that's already written there,
Mm-hmm.
it's sine A cos B plus cos A sine B, and then on the bottom it's cos A cos B minus sine A sine B, and then we did coses on the bottom.
So, okay, so this guy right here is right here and is right here, right?
Yeah.
And so the only thing that's new is this being added in is weird. And I said that's something that's kind of, they're doing an operation to help fully simplify this that I don't expect you to know how to get that. So the cos A, cos B on the bottom here just showed up. Just kind of don't let that bother you. But what I do want to do is this simplifying, if you're good here, that's really all I care about. If you see how this got to that, that's what I kind of think is important. So this being able to cancel,
Yeah.
that's a tangent.
Yeah.
That being able to cancel, that's a tangent.
Yeah.
Those cancel all the way, that's a 1. And then these are 2 tangents. That's what I kind of care about. If you, like I said, if you don't understand, like if you don't understand this part, fully understand that. But all that happened was, if you're good here, you know where these came from, right? That's from the top, right? So this is now over here. This is now over that. So they put cos A, cos B below both of those numerator and denominator. That's the weird part. And I think that's where most of you don't like. That's fine. Okay? We can still talk about more. But again, maybe I should skip it. I don't know. It's not super important. So the A minus B one, maybe, again, if this is bothering you, maybe, Matt, you can just watch. You don't have to write if it's going to bother you. Because I don't want it to bother you.
I just don't get where, why all of a sudden cos A and cos B is all of a sudden on the bottom, but then
Right.
that's why I'm...
Yes, and I fully understand that, and I actually don't even have an explanation other than they're using that because it helps us fully simplify it. So they got it because they knew that those cancelings would happen. So that's what I'm saying. That cos A, cos B essentially came from nowhere in terms of trying stuff. Like when you're doing identity stuff and trying to fully simplify stuff, that's going to be one of the very high level one of where you're proving something that's, it's getting you to tangent. So you can do anything you want in identity as long as you do it to everything, and that's just a case of doing that. Why would you do that? I don't know. Why they did cos A, B? They're going to do it again here. They're going to do it again here. So this will be the same cos A, cos B. So A minus B, that's what we're doing. And so we're going to do it again. We're going to write that as tan, sine A minus B cosine A minus B. Okay, so then we're going to write our sum differences that we just learned. So for sine, it's going to be sine A cos B minus cos A sine B all over. The cos is cos A cos B plus sine A sine B. For proving these?
No, how you put it over cos A cos B and all that, you just do that for this.
Yes, that's what I'm saying. For proving these tangents, that's what they did both times, yes. So we're doing the same strategy. So that's why I was saying the thing that Matt didn't like is going to happen again. So they're going to go sine A cos B. And you're not the only one, Maddie. Right. And to be honest, like, well, I know why they're doing it. They're doing it because this is what gets us to simplify it into the formula. It's like, where does it come from is the, like, yeah, that's valid. And that's why I'm saying maybe I'll do a little research to try to get some more information on that.
Yeah, but then all of a sudden there's no more signs on the bottom. Like, that screws my brain. Honestly.
Well, those go away because of the tangent conversions, but yeah. So I'm just writing them as the 4 fractions like we just had before so you can see the cancels. Again, if you just want to swatch, that's totally fine. Okay, so there, and nothing there. Very similar breakdown. So then we have the top is going to be tan A minus tan B. The bottom is going to be 1 plus tan A tan B. And so that's right there. Okay. And then we'll get to some actual examples here that aren't as much proving it, so hopefully that will help. Okay. So, yeah, wait, sure. All right, so let's get to the last part here. So it's got the examples now. So now, where do we use these? So we actually use these. This is important because a few of you had talked about in your test avoided exact value again. You just calculate a calculator for everything. So these can help you get exact values for numbers, some degree measures that are not on the unit circle. Like 15 degrees is not in the unit circle. But we could write this as sine 45 minus 30. Sine of 45 minus 30 is 15. And so then we can go ahead and write our sum difference. So it would be sine of 45 cos of 30 minus sine of 30, or it says you're supposed to go cos of 45, aren't you? But it doesn't really matter. Okay. Okay. Cos of 45 sine of 30. Because these, why is that helpful? Because we can get exact values for these. These are on our unit circle. Yeah, so sine of 45, root 2 over 2. Yeah. Cos of 30, root 3 over 2. Minus cos of 45, root 2 over 2. Sine of 30, 1/2. So when you do that, it's going to be root 6 over 4 minus root 2 over 4. You can't subtract radicals with radicans like that, so you just have to write it as root 6 minus root 2 over 4. That's the exact value. Okay, questions there? Now, I know it's going to drive you nuts, and probably especially Hannah, but all of you. Okay, 5 pi over 12. You want to think about how can I break 5 pi over 12 into values from the unit circle, because 5 pi over 12 is not in the unit circle. Okay, so what you can do in these is that we know that the cuts that we deal with are in what? They're in 3s, 4s, and 6s. 2s as well, but we don't use 2 for right now. So what I'm saying is write pi over 3 with 12ths. I know you guys hate that. How would you write pi over 3 with 12ths? 4 pi over 12, right? Pi over 3 equals 4 pi over 12. They're the same thing. Okay, how about for pi over 4? And then for 6. Okay, now, which of those two added will give me 5 pi over 12? Right, these two, pi over 4s and pi over 6. So 3 pi over 12 plus 2 pi over 12, correct. So we will write this as, they're saying cotangent, which is fine. So we're going to do cotangent pi over 4 plus pi over 6. Okay. Now, let's see if you guys can understand this. Cotangent we know is 1 over tangent, right? So what we're going to do is we're going to take the tangent formula for addition that's a fraction and do what to it? Flip it. So what I'm saying is normally, I'll write it right here, the normal tan that we just learned a second ago for addition was this. Tan A plus tan B all over 1 minus tan AB. And so, or tan A, tan B, sorry. So we're going to flip this because it's cotangent. So we're going to flip that. Okay? So that means we're going to have this. We're going to have 1 minus tan pi over 4, tan pi over 6, all over tan pi over 4 plus tan pi over 6. And now we can find those exact values. Yep. So see how it's 1 over tan? Yeah. That right there is a sum formula for tangent. Yeah. That's what that formula is. But since it's 1 over it, I'm going to flip our tan formula. So I flipped, see the 1 minus is on the top now.
So why did it stay on, I understand that, but why did it stay tan A plus tan B on the bottom? Like why did
Oh,
if you flipped it, I thought it would just be over 1.
You flipped it be over 1. Oh, no, because this is 1 over tangent. That means inverse of tangent, like flip reciprocal of tangent.
Yeah.
So we're taking the reciprocal of the tan identity. So there's no 1. Okay? Because this right here equals the tan A plus B. So if I want to do tan 1 over tan A plus B, I need to flip that. So we flip this. That's all we have to do. The 1's not really relevant anymore. The 1 over just tells you it's the reciprocal, Hannah. So you want the reciprocal of the formula. Okay, and then I plugged in the values. Okay, pi over 4, that's a good one for tangent. That's because tangent pi over 4 is good. 1. So you have 1 minus 1. What's tangent at pi over 6? So that's the 1/2 over root 3 over 2. So that's the root 3 over 3, right? Because you'll rationalize. Remember? It's on the front page too. But. Okay. Tangent at pi over 6 is root 3 over 3. It's on the front page. So root 3 over 3 here. Okay, and the bottom is 1 again, plus root 3 over 3. So you have 1 minus root 3 over 3 and 1 plus root 3 over 3. Okay? So I don't mind it staying like this. You can get a common denominator and make this one fraction. The book does this, so I'll just show you, but I don't really like that they did this. But so they times root 3 to top and bottom. So when they do that, it does hit everything, right? It hits here, hits there, and hits there. So then they're left with root 3. Well, what's root 3 times root 3? And then it's 3 over 3. So it's minus 1. And then it's root 3 on the bottom. I'm going to round root, and it's plus 1. So their answer was root 3 minus 1, root 3 plus 1. Okay? I wouldn't have minded. Last class, we actually did do this is a common denominator of 3 over 3. And put that together, that's fine too, because then the 3's cancel. So again, kind of the simplifying there, you kind of go either way. I'm not too picky on that. Okay? Okay, got a couple more. Last 2. Okay, simplify the following. Sine of 100 cos of 10 minus cos of 100 sine of 10. So the idea is here, if you see something like this on like a diploma exam, is like, oh, that looks like a sum or identity. So if it's written like this, then we should be thinking, okay, it's sine, cos, cosine. So is that a cos or a sine formula? sine, and then that means it's a subtraction. You're simply going to do this. You're going to go the other way because we can get this exact value. Done. So that mess is 1 pretty quickly. Okay? Now, two things, if you're saying, wait a second, we just practiced on doing some difference to get exact values with using the formulas. Now you're saying to undo the formula. Good question. The reason I'm undoing is this because sine of 100, is that exact? No, that's not a nice spot for us. Either's 10. But I do know that 100 minus 10 is 90. And I'm like, oh, I like 90. Okay? Now this one even looks weirder. This would be a good diploma of excellence question because it's got a variable in there for you. Focus on the pattern. The pattern is cos, cos, sine, sine. So I know it's a cos one. And then it's a minus, which means it's a plus. So this is the cos a plus b form. What's my a? People keep thinking that. It's just this whole thing. That's a, cos b. So it's the 1/4 pi minus. So watch. Cos 1/4 pi minus theta is my a, plus 1/4 pi plus theta is my b. So this little chunk's my a, that little chunk's my b. Do you see what, like, I know it looks confusing, but what happens quickly? Negative theta, positive theta, that whole theta problem's gone. So 1/4 plus 1/4 is the math you're doing. 1/4 plus 1/4 is 2/4. So cosine of pi over 2, oh cool, because we know what that is. 0. Because cosine at pi over 2 is 0. You're at the top. All right, last one here. This one's a little bit of bringing it all together. Okay, I kind of like this one, actually. Okay, a lot of you guys aren't reading these very well, and that's just me being honest. Okay, know what that means. What that means right there, if a is between 0 and pi over 2, a is in quadrant 1. If b is between 2 pi and 3 pi over 2, b is in quadrant 2. Or 4, I mean, sorry. That's what that stuff means. Does that make sense? I'm just showing you that because that's going to affect your answers. Okay, so it now says that cos of a and cos of b is 3 over 5 and 5 over 13. So we want to do cos of a plus b, and that's fine. But if I do cos of a plus b, we know that form is cos a, cos b, minus sine a, sine b. However, we only know what cos A and cos B are. We don't know what sine A and sine B are. So what are we missing? Let me take it further. For A, we know that that's a ratio of 3 over 5. What's the 3 in the ratio for cosine? X. What's the 5? R. We need y for sine, right? Right, so we're going to do Pythagorean Theorem. 3 squared plus y squared equals 5 squared. 3 and 5 is a pretty common one, right? What's the y? You guys remember? 4, right? 3, 4, 5. 3, 4, 5 is the easiest Pythagorean triple you'll know. Another way you can find this is 25 minus 9 is 16 square root 4. So my point is 4 is y. If you need to write your Pythagorean Theorem all the way out, that's fine. Okay? If I'm rushing you, don't worry about that part. I know you can use Pythagorean Theorem. Okay? So we just figured out what 4 is y for a. So that helps us do sine a now. We know what sine a's value is. Okay? Now, for b, it's 5 and 13. So x is 5, r is 13. So you're going to do 13 squared minus 5 squared to get what your y is. 13 squared minus 5 squared is 169 minus 25, 144. Y is 12 for b. And it's not just positive 12 because of y. It's in the 4th quadrant, so sine's negative down there. So negative 12. Okay? So, the thing you got to realize is that these are actually values. Cosine of A equals 3/5. So that means this is a 3/5 to us.
We don't write cos 3/5.
No, because the cos A is 3/5, exactly.
Okay.
That's why I said it that way. Cos A is 3/5. Okay? Cos B, 5/13. What is sine A? 4/5. Good work. That's a 13 there, sorry. Not a very good one. 4/5 is sine A, and sine B, negative 12/13. And now we're just going to go ahead and get this together. So 15/65 plus, because negative times a negative, 48/65, which is nice to give that common denominator set up already. And we get 63/65 is that exact answer. Okay. All right, we'll stop there for that one.